Hi dear students. So in this class, in this lecture, we'll be discussing a very comprehensive topic, which is classification of marine sediments, which is again in continuum with the subject oceanographic lecture series. So this lecture is going to be very comprehensive, so you have to bear with me, and I advise you to play at 1.5x or 2x speed on YouTube. So Uh, talking about the classification of marine sediments, so we have different type of sediments. Number one, we have lithogenous sediments, we have biogenous sediments, we have chemically precipitated sediments which are made from the chemical reactions, and then we have some cosmogenic sediments as well in the marine realm. So starting from the lithogenous sediments, what are the characteristics of lithogenous sediments? So lithogenous sediment, it literally translates into a sediment which is produced from the stone. Lithos means stone and generate it is to produce. So lithogenous sediment is derived from pre-existing rock material that originates on the continents or islands from erosion, volcanic eruptions, or blown dust. So lithogenous sediment is sometimes referred to as tertigenous sediments as well. So tertigenous, terra means land and generate means to produce. So in the right, we can see the you can see a picture here, so which is a typical ocean floor covered by a thick blanket of fine particles that have slowly settled onto the seafloor with the process of suspension settling. And the depression, mounds, and tracks, these are made by bottom dwelling organisms. So there is this crab which is around 4 inches, and we have depressions, we have mounds, we have tracks as well. So a lot of features on the seafloor. So what is the origin of lithogenous sediment? How is it originate? How does it originate? So it begins as rocks, lithogenous sediment on continents or islands, and over the time, weathering agents such as water, temperature extremes, highs and lows of the temperatures, and chemical effects, they break these rocks into small pieces, and these rocks in smaller pieces, when are in smaller pieces, they can be easily eroded, picked up, and transported. And this eroded material, which is, it forms the basic component of all lithogenous sediment. So this eroded material from the continents is carried to the oceans by the streams, wind, glaciers, and gravity. And each year, stream flow alone carries about 20 billion metric tons of sediment to Earth's continental margins, and almost 40% of that is provided by runoff from Asia alone. So transported sediments, they can be deposited. Once transported, they can be deposited in many environments, including bays or lagoons near the ocean, as deltas at the mouth of the rivers, along beaches at the shorelines, or further offshore across the continental margin. So it can also be carried beyond the continental margin into the deep ocean basin by turbidity currents, as we have previously discussed in other lectures. So this is a picture which is demonstrating the origin of the lithogenous sediment. It's a normal outcrop. So over time, fractures develop and weathering occurs along these fractures. And these fractures, these breaks rocks into the smaller fragments, which are much easier to transport over a period of time. So this is this figure, it is uh, light color. You can see it is the suspended sediment in the water, which is brought up by this river here in the picture. And the stream, this is actually Po River in Italy, which displays the prominent delta and a visible sediment plume in the water. So this is again a whole delta, and we have sediment plume. And then we have dust storms approaching a military base. So dust can also contribute to the lithogenous sediment in the oceans. And now in the sea, we can see this is a glacier, and the dark stripe is the sediment or the crushed rock debris, which is called a medial moraine. So we have some debris in the sides, we can call it as a terminal moraine. So in the center, we have the medial moraine, and this is again the sediment which is under action of gravity. It's created a landslide created by the gravity. So this slide eventually, shows us the different sources of terrigenous sediments or lithogenous sediments in the marine. So Talking about in detail the composition of lithogenous sediment. So this is what a magnified image of a lithogenous beach sand it looks like. So it is a well sorted, I mean, all the grains, they are equal in size almost. So which is composed mostly of particles of white quartz, which is the white glass-like substance, small beads, plus small amounts of other minerals. And this sand is from North Beach, Hampton, New Hampshire, and is magnified approximately 23 times. So the composition of lithogenous sediment reflects the material from which it was derived. Obviously, all rock composed of discrete crystals of naturally occurring compounds called minerals, and one of the most abundant chemically stable and durable mineral in Earth's crust is quartz, composed of silicon and oxygen in the form of SiO2. And the same composition which is as ordinary glass. So quartz is a major component of most rocks because quartz is resistant to abrasion. It can be transported long distances and deposited far from its source area because it cannot be broken down completely. The majority of lithogenous sediments such as beach sands are composed primarily of quartz. So moving next, uh, it is here in this picture we can see portion from the Sahara, from the African continent, smaller from the Europe and even from the North America, how the wind is blowing and carrying the sediments into the Atlantic Ocean. So we have a large percentage of lithogenous sediments or particles that find their way into the deep ocean. They come uh, into the deep ocean sediments far from continents are transported by prevailing winds that remove small particles from the continent subtropical desert regions. So this map in the figure, it shows a close relationship between the location of microscopic fragments of lithogenous quartz in the surface sediments of the ocean floor and the strong prevailing winds in the desert regions of Africa, Asia, and Australia. So satellite observations of dust storms confirm this relationship, and sediment is not only the item transported by the wind. In fact, scientists have documented transportation of a variety of airborne substances, including viruses, pollutants, and even living insects from Africa all the way across the Atlantic Ocean to North America. So now let's discuss about the distribution of lithogenous sediments, how the lithogenous sediments they are distributed. So these marine sedimentary deposits, they can be categorized either neritic or pelagic based on the depth. Neritic means off the coast, are found on continental shelves and in shallow water near islands. These deposits are generally coast-grained, and alternatively pelagic, pelagios means off the sea, neritic means off the coast. So pelagic deposits are found in deep ocean basins and are typically fine-grained. And moreover, lithogenous sediments in the ocean is ubiquitous. At least a small percentage of lithogenous sediment is found nearly everywhere on the ocean floor. So now let's discuss about the neritic deposits. So lithogenous sediment dominate most neritic deposits, and the lithogenous sediment is derived from rocks from the nearby land masses, consists of coarse grain deposits, and accumulate rapidly on the continental shelf slope and rise. So what are the examples? Examples of lithogenous neritic deposits, they include beach deposits, continental shelf deposits, turbidite deposits, and glacial deposits. So number one, beach deposits. Beaches are made of whatever materials they are locally available. Beach materials are composed mostly of quartz-rich sand that is washed down to the coast by rivers, but can also be composed of a wide variety of sizes and compositions. So this material is transported by waves that crash against the shoreline, especially during storms. Now, continental shelf deposits. So at the end of the last ice age, about 10,000 years ago, glaciers melted and sea level rose. As a result, many rivers of the world today drop their sediment in the drowned river mouths rather than carry out onto the continental shelf as they did during the geological past. So this explains why in many areas the sediments that cover the continental shelf called relict means left behind sediments were deposited from 3,000 to 7,000 years ago. and are not covered by the sediments discharged by the rivers today. So these relict sediments presently cover about 70% of the world's continental shells. In other areas, deposits of sand ridges on the continental shelves appear to have been formed more recently than the most recent ice age at present water depths. Okay. Now, turbidite deposits. So, turbidity currents, as we have seen in previous lectures as well, these are underwater avalanches that periodically move down the continental slopes and carve submarine canyons. So, turbidity currents also carry vast amounts of neritic material. This material spreads out as deep sea fans, comprises the continental rise, and gradually thins towards the abyssal plains. So these deposits are called turbidite deposits and are composed of characteristic layering called graded bedding. Now, last from the neritic deposit is glacial deposits. So poorly sorted deposits containing particles ranging from boulders to clays may be found in high altitude portions of the continental shelf. These glacial deposits were laid down during the most recent ice age by glaciers that covered the continental shelf and eventually melted. And the glacial deposits are currently forming around the continent of Antarctica and around Greenland by ice rafting. In this process, rock particles trapped in glacial ice are carried out to the sea by icebergs that break away from coastal glaciers. As the icebergs melt, lithogenous particles of many sizes are released and settle onto the ocean floor. Now let's discuss about the pelagic deposits. So turbidite deposits of neritic sediment on the continental rise can spill over into the deep ocean basin. However, most pelagic deposits are composed of fine-grained materials that accumulate slowly on the ocean floor. Pelagic lithogenous sediment include particles that have come from volcanic eruptions, wind-blown dust, and fine material that is carried by deep ocean currents. So next is abyssal clay. Abyssal clay is composed of at least 70% by weight fine clay-sized particles from the continents. Even though they are far from land, deep abyssal plains contain thick sequences of abyssal clay deposits composed of particles transported great distances by winds or ocean currents and deposited on the deep ocean floor. Because abyssal clays contain oxidized iron, they are commonly red, brown, or buff in color and are sometimes referred to as red clays. So, the predominance of abyssal clay on abyssal plains is caused not by the abundance of clay settling on the ocean floor, but by the absence of other material that would otherwise dilute it. Now, number two, which is really interesting after lithogenous, is the biogenous sediment. So what are the characteristics of biogenous sediment? So biogenous sediment, bio means life, generate means to produce. So it is called biogenic sediment. It is derived from the remains of hard parts of once living organisms. So what is the origin of these biogenous sediments? So biogenous sediments begins as hard parts like shells, bones and teeth of living organisms ranging from minute algae and protozoans to fish and whales. When organisms that produce hard parts die, their remains settle onto the ocean floor and can accumulate as biogenous sediment. So the biogenous sediment can further be classified as either macroscopic or microscopic. Macroscopic biogenous sediment is large enough to be seen without the aid of a microscope and includes shells, bones, and teeth of large organisms. Except in certain tropical beach localities where shells and coral fragments are numerous, this type of sediment is relatively rare in marine environment, especially in deep water where only few organisms live. So much more about the microscopic biogenous sediment. These are much more abundant, which contains particles so small that can be well seen only through a microscope. Microscopic organisms produce tiny shells called tests. Test, which testa comes the word from a testa, which translates to shell, and they begin to sink after the organisms die and continually rain down in great numbers onto the ocean floor. These microscopic tests can accumulate on the deep ocean floor and form deposits called ooze. So ooze comes from a word woos, which translates to the juice. As the name implies, ooze resembles very fine-grained mushy material, and technically biogenous ooze must contain at least 30% of biogenous test material by weight. So the other part, 70%, it is fine-grained lithogenous clay that is deposited along with the biogenous test in the deep ocean. By volume, much more microscopic ooze than macroscopic biogenous sediment exists on the ocean floor. The organisms that contribute to biogenous sediment are chiefly algae and protozoans. So algae are primarily aquatic, eukaryotic, photosynthetic organisms ranging in size from microscopic single cells to large organisms like giant kelp. And protozoans are any of the large group of single-celled eukaryotic, usually microscopic organisms that are generally not photosynthetic. So the composition of biogenous sediment, the two most chemical compounds in uh, biogenous sediments are calcium carbonate, CaCO3, which forms the mineral calcite, and silica, SiO2. Often the silica is chemically combined with water to produce SiO2 and n times water, the hydrated form of silica, which is called opal, which is a gem variety of silica, which is predominantly used in jewelry and etc. So now let's talk about the silica. Most of the silica in biogenous ooze comes from microscopic algae. This is called diatoms. So diatom word comes from diatoma, which means cut in half, and protozoans called radiolarians. So radio, a spoke or a ray. So two organisms they contribute to the silica. Number one, algae, microscopic algae called diatom, which we can see in the figure here as well. Diatom, two parts of the diatom test, they are fitting each one, looking like a capsule. And number one and number two are protozoans called radiolarians, which are a spoke or ray-like, which we will see in the next slides. So these diatoms, they photosynthesize and they need strong, because they photosynthesize, they need strong sunlight and are found only within the upper sunlit surfaces of the water. So most diatoms are free floating or planktonic. Planktons means they are wander around. The living organisms builds a glass greenhouse out of silica as a protective covering and lives inside. So most species have two parts of their test that fit together like a petri dish or pillbox. The tiny tests are perforated with small holes, as you can see in these figures, in intricate patterns to allow nutrient to pass in and waste products to pass out. So when diatoms are abundant at the ocean surface, thick deposits of diatom-rich ooze can accumulate below the ocean floor. When this ooze lithifies, it becomes diatomaceous earth, a lightweight white rock composed of diatom tests and clay, which has the economic importance as well. Now, coming to the radiolarians, which are microscopic single-celled protozoans, most of which are also planktonic, and as their name implies, they often have long spikes or rays of silica protruding from their siliceous cells. You can see these spikes. Okay, so they do not photosynthesize but rely on external food sources such as bacteria or other planktons. And radiolarians typically display well-developed symmetry, which is why they have been described as the living snowflakes of the sea. The accumulation of siliceous tests of diatoms, radiolarians, and other silica-secreting organisms produces siliceous ooze. You can see here magnified image of a siliceous ooze. You can see some fragments of diatoms as well, some radiolarians as well, but mostly these are diatom fragments in this picture. Okay, now let's talk about calcium carbonate. So two significant sources of calcium carbonate biogenous ooze are foraminifers, so which translates from a foramen, that means an opening. So these are the organisms with a opening, so which are who are close relatives to radiolarians, and microscopic algae called coccolithophores. Coccus means berry, lithos means stone, and Freud means carrying. So coccolithophores are single-celled algae, most of which are planktonic. So coccolithophores produce thin plates or shields made up of calcium carbonate, 20 or 30 of which overlap to produce a spherical test. I'll see a figure, it's very beautiful. Like diatoms, coccolithophores photosynthesize, so they need sunlight to live. Coccolithophores are really small. In fact, coccolithophores are about 10 to 100 times smaller than most diatoms, which is why coccolithophores are often called as nanoplanktons. Nano means dwarf, planktons means wandering. Here you can see a picture of a coccolithophore. In A, here about 20 plates they are combining to form a single test, small, made up of tiny spheres. So this image is about 10 microns. Now diatom, you can see there is a single diatom here surrounded by coccoliths, which are calcareous. This is siliceous in nature, the diatom with perforations, and surrounded by small RBCs looking like, which are calcareous in nature, coccoliths. And then this is an image of foraminifers, which resembles shells found at the beach. These are all forams, and you can see the scale, 100 microns. And now this is a calcareous ooze, which also includes some siliceous radiolarian turf. So these are foraminifers, these organisms, and radiolarians are like these net or meshy shaped, which are silica rich. So what happens is when the organism dies, the individual plates called coccoliths, they disaggregate and they accumulate on the ocean floor as coccolith rich ooze. When this ooze lithifies over time, it forms a white deposit called chalk, which is used for a variety of purposes, including writing on the chalkboards. The White Cliffs of southern England are composed of hardened coccolith-rich calcium carbonate ooze, which was deposited on the ocean floor and has been uplifted onto the land. And this area is very scenic. Most of the movies or multimedias they go to this place, these White Cliffs, because they are very beautiful. Deposits of chalk the same age as the White Cliffs are so common throughout the Europe, North America, Australia, and Middle East that the geologic period in which these deposits formed is named Cretaceous. Creta means chalk. Cretaceous period. So on the geological time scale, the Cretaceous period has been named after the chalks, because around this same age all across, I mean, majority of the continents, we do see these chalk deposits. So now foraminifers, they are single cell protozoans, many of which are planktonic, ranging in size from microscopic to macroscopic. They do not photosynthesize, so they must ingest other organisms for food. And foraminifers, they produce a hard calcium carbonate test in which the organism lives. And most foraminifers produce a segmented or chambered test, and all tests have a prominent opening in one end. Although very small in size, the tests of foraminifers resemble the large shells that one might find at the beach. So deposits comprised primarily of tests of foraminifers, coccoliths, and other calcareous secreting organisms are called calcareous ooze. So this is a picture of White Cliffs of southern England. You can see the White Cliffs. It is mostly composed of coccolithophores, the various small plates. They form like a sphere. So this is the White Cliff, Strait of Dover in England. So now let's talk about the distribution of biogenous sediment. How is it distributed? So biogenous sediment is one of the most common types of pelagic deposits. I mean, these are the deposits that reach into the deep ocean floor. The distribution of biogenous sediment on the ocean floor depends on three fundamental processes. Number one, productivity, destruction, and dilution. So productivity is the number of organisms present in the surface water above the ocean floor. And surface waters with high biologic productivity contain many living and reproducing organisms, and conditions that are likely to produce biogenous sediments. Conversely, surface waters with low biologic productivity contain too few organisms to produce biogenous oozes on the ocean floor. Number two, destruction occurs when skeletal remains dissolved in seawater at depth. In some cases, biogenous sediment dissolved before ever reaching the sea floor. In other cases, it is dissolved before it has a chance to accumulate in the deposits, into the deposits on the sea floor. Number three, dilution. Dilution occurs when the deposition of other sediments decreases the percentages of the biogenous sediment found in marine deposits. For example, other types of sediments can dilute biogenous test material below 30%, which is the necessary criteria to classify it as a ooze. Dilution occurs most often because of the abundance of coarse-grained lithogenous material in neritic environments. So biogenous oozes are uncommon along continental margin because there is a lot of dilution going on. Now let's talk about the neritic deposits. Neritic deposits of biogenous. The neritic deposits are dominated by lithogenous sediment. Both microscopic and macroscopic biogenous material may also be incorporated into lithogenous sediments and neritic deposits. In addition, biogenous carbonate deposits are common in some areas. So, carbonate deposits. Carbonate minerals are those that contain CO3 in their chemical formula, such as calcium carbonate, CaCO3. Rocks from the marine environment composed primarily of calcium carbonate are called limestones. Most limestones they contain fossil marine shells suggesting a biogenous origin, while other carbonate containing rocks appear to have formed directly from seawater without the help of any marine organism. Modern environments where calcium carbonate is currently being deposited, such as the Bahama Banks, Australia's Great Barrier Reef, and the Persian Gulf, suggests that carbonate deposits are formed in shallow, warm water shells around tropical islands as coral reefs and beaches. Ancient marine carbonate deposits constitute 20% of Earth's crust and 25% of all sedimentary rocks on Earth. In fact, marine limestones from the underlying bedrock of Florida and many Midwestern states from Kentucky to Michigan and from Pennsylvania to Colorado. Percolation of groundwater through these deposits has dissolved the limestone to produce sinkholes and, in some cases, spectacular caverns. Stromatolites. So stromatolites, they are lobate structures consisting of fine layers of carbonate that form in specific warm, shallow water environments such as high salinity tidal pools in Shark Bay, Western Australia. So in the right, you can see the profile view of a stromatolite showing its layers of algae. So these are stromatolites and Shark Bay stromatolites which form in high salinity tidal pools. So how are these stromatolites formed? These are basically cyanobacteria. They produce these deposits by trapping fine sediments in mucus mats. Other types of algae produce long filaments that bind carbonate particles together. Like tree rings have been added as a tree grows, layer upon layer of these algae colonize the surface, forming a bulbous structure. Like here, you can see in the figure, bulbous structure. In the geologic past, particularly from 1 to 3 billion years ago, conditions were ideal for the development of stromatolites. So stromatolite structures hundreds of meters high can be found in rocks from these ages. Now let's talk about pelagic deposits. So microscopic biogenic sediment ooze is common in the deep ocean floor because there is so little lithogenous sediment deposited at great distances from the continents that could dilute the biogenous material. So siliceous ooze, it contains at least 30% of the hard remains of silica secreting organisms. When the siliceous ooze consists mostly of diatoms, it's called diatomaceous ooze. When it consists mostly of radiolarians, it's called radiolarian ooze. When it consists mostly of single-celled silicoflagellates, another type of protozoan, it is called silicoflagellate ooze. So, how this siliceous ooze accumulates is you can see if there is an area of low productivity. So we have few silica tests sinking, and when they sink, they dissolve as well. So there is the rate of supply of silica tests is less than the rate at which silica dissolves. So there is no silica ooze. Whereas in the area of high productivity, silica secreting organisms live in sunlit surface waters. Siliceous ooze only accumulates beneath those areas where productivity is high. So we have high productivity area. So we have many silica tests sinking here, and the silica tests accumulates above the abyssal clay. Here the rate of supply of siliceous tests is greater than the rate at which silica dissolves. So hence siliceous ooze accumulates. So the ocean is undersaturated with silica at all depths, which means that any solid particle made up of silica will tend to dissolve in seawater. In fact, if living diatoms, radiolarians, and silicoflagellates were not hard at work creating their silica-containing tests, they would dissolve too. As a consequence, the destruction of siliceous biogenous particles by dissolving in seawater occurs continuously and slowly at all depths. So how can the siliceous ooze accumulate? One way is to accumulate the silica tests faster than the seawater can dissolve them. So for instance, many tests sinking at the same time will create a deposit of siliceous ooze on the seafloor below. Once buried beneath other siliceous tests, they are no longer exposed to the dissolving effects of seawater. Thus, siliceous ooze is commonly found in areas below surface waters with high biologic productivity of silica secreting organisms. So, calcareous ooze and the carbonate compensation depth. So, calcareous ooze contain at least 30% of the hard remains of calcareous secreting organism. When it consists mostly of coccolithophores, it is called coccolith ooze. When it consists mostly of foraminifers, it is called foraminifer ooze. One of the most common types of foraminifer ooze is Globigerina ooze, named for a foraminifer that is especially widespread in the Atlantic and South Pacific Oceans. Other calcareous ooze include pteropod oozes and ostracod oozes. So the destruction of calcium carbonate, like silica, it varies with depth. At the warmer surface and in the shallow parts of the ocean, seawater is generally saturated with calcium carbonate, so calcite does not dissolve. In deep ocean, however, the colder water contains greater amount of carbon dioxide, which forms carbonic acid and causes calcareous material to dissolve. The higher pressure at depth also helps speed the dissolution of calcium carbonate. So you can see here in the figure, ocean pressure increases and the properties of seawater change below the CCD, affecting where calcite dissolves and where it is deposited. So we have calcareous phytoplanktons living in the sunlit surface waters. So they die and their tests they fall along. So above the CCD, calcite is stable and is not dissolved, which is along 4.3 kilometers. And below that, below this depth, calcite compensation depth, we have ocean conditions. They cause calcite to dissolve rapidly. So what are the conditions below the CCD? We have lower temperature, we have higher pressure, we have high CO2, and we have low pH, which means more acidic environment. So the depth in the ocean at which the pressure is high enough and the amount of carbon dioxide in deep ocean waters is great enough to begin dissolving of calciocarbonate and is called as lysocline. So a loosening slope. Below the lysocline, calcium carbonate dissolves at an increasing rate with increasing depth until the CCD is reached, which is calcite compensation depth. At the CCD and greater depths, sediment does not usually contain much calcite because it readily dissolves. Even the thick tests of foraminifers dissolve within a day or two. In essence, calcite accumulates only near the tops of the tall peaks that rise above the seafloor and extend above the CCD, but dissolves at deeper depths associated with the bakes of the peaks. This situation creates the marine equivalent of a mountain snow line, but with deposits of light-colored calcite on the mountain top instead of frozen water. So the CCD on average is 4,500 meters or 4.5 kilometers below sea level, but depending on the chemistry of the deep ocean, it may be as deep as 6,000 meters in portions of the Atlantic Ocean or as shallow as 3,500 meters in the Pacific Ocean. So the depth of the lysocline also varies from ocean to ocean, but averages around about 4,000 meters. So this is the distribution of biogenous sediment. Uh, you can see the dark orange color. These are greater than 80% by weight. And then as the lighter shade appears, lighter orange, it is 50 to 80% by weight. And in the blue shade, it is less than 50% by weight. So you can see mostly along the divergent margins, we have high percentages. Excuse me. So you can see along the Pacific Ocean and the Atlantic Ocean, we have 50 to 80% by weight uh, calcareous ooze. So distribution of calcium carbonate. Now let's talk about hydrogenous sediment. Hydrogenous sediment, it is hydro means water, generates to produce, is dissolved, derived from the dissolved material in water. So what is the origin of hydrogenous sediment? So seawater, it contains many dissolved materials. So chemical reactions within seawater cause certain minerals to come out of the solution or precipitate. Precipitation usually occurs when there is a change in conditions such as change in temperature or pressure or the addition of chemically active fluids. To make rock candy, for instance, a pan of water is heated and sugar is added. When the water is hot and sugar dissolved, the pan is removed from the heat and the sugar water is allowed to cool. The change in temperature causes the sugar to become oversaturated, which causes it to precipitate. As the water cools, the sugar precipitates on anything that is put in the pan, such as the pieces of string or kitchen utensils, जिसको हम अपनी local language में मिश्री भी कहते हैं, जैसे मिश्री बनाई जाती है. So, composition and distribution of hydrogenous sediments. So, although hydrogenous sediments represent a relatively small portion of overall sediment in the ocean, they have many different compositions that are distributed in different diverse environments of deposition. So, number one is manganese nodules. So, these manganese nodules, they are rounded, hard lumps of manganese, iron, and other metals, typically 5 centimeters in diameter, up to a maximum of about 20 centimeters. So when cut in half, they often reveal a layered structure formed by precipitation along a central nucleation object. So the nucleation object may be a piece of lithogenous sediment, coral, volcanic rock, a fish bone, or a shark's tooth. You can see here in the figure, these are manganese nodules, and when we have a cross section, so we can see a layered structure around a nucleus. So at the bottom, it is the abundance of a manganese nodules in the portion of a deep South Pacific Ocean floor. So manganese nodules, they lie on sediment in vast expanses of abyssal plains, potentially covering some 60% of the ocean basin at a typical water depth of about 5 kilometers. Manganese nodules can sometimes occur in concentrations of about 100 nodules per square meter. In rare cases, they exist in even greater abundance. Resembling a scattered field of golf ball to baseball sized nodules, the formation of nodules requires extremely low rates of lithogenous or biogenous input so that the nodules are not buried. So here you can see in this picture how these nodules are spread along the ocean floor, distributed. So the major components of these nodules are manganese hydroxide, around 30% by weight, and iron hydroxide, around 20%. The element manganese is important for making high-strength steel alloys. Other accessory metals present in manganese nodules include copper, which is used in electric wiring, in pipes, and to make brass and bronze, nickel, which is used to make stainless steel, and cobalt, used in allied with iron to make strong magnets and steel tools. Although the concentration of these accessory metals is usually less than 1%, they can exceed 2% by weight, which may make them attractive sources of these metals in the future. Number two is your phosphates. Phosphorus bearing compounds, they are called phosphates. They occur abundantly as coatings on rocks and as nodules on the continental shelves and on banks at depths shallower than 1000 meters. Concentrations of phosphates in such deposits commonly reach 30% by weight and indicate abundant biological activity in surface water above where they accumulate. Because phosphates are valuable as fertilizers, ancient marine phosphate deposits that have been uplifted onto land are extensively mined to supply agricultural needs. Carbonates. The two most important carbonate minerals in marine sediments are calcite and aragonite. Both are composed of calcium carbonate, CaCO3, but aragonite has a different crystalline structure that is less stable and transforms into calcite over time. Carbonates are usually used in construction industry, in the production of cement, and they are commonly used medicinally as calcium supplements or antacids. As previously discussed, most carbonate deposits are biogenous in origin. However, hydrogenous carbonates deposits can precipitate directly from seawater in tropical climate to form aragonite crystals less than 2 millimeters long. In addition, oolites, which are O means egg, lithos means rock, they are small calcite spheres 2 millimeters or less in diameter and that have layers like an onion and form in some shallow tropical waters where concentrations of CaCO3 are high. Oolites are thought to have precipitate around a nucleus and grow larger as they roll back and forth on beaches by wave action. But some evidence suggests they are a type of algae. A type of algae may aid their formation. Number three is now metal sulfides. Deposits of metal sulfides are associated with hydrothermal vents and black smokers. Uh, Along with the mid-ocean ridge, these deposits they contain iron, nickel, copper, zinc, silver, and other metals in varying proportions. And transported away from the mid-ocean ridge by seafloor spreading, these deposits can found throughout the ocean floor and can be uplifted onto the continents as well. Evaporites. Generally, evaporites minerals form wherever there are high evaporation rates, which means dry climates accompanied by restricted open ocean circulation. One such example is the Mediterranean Sea, which contains thick deposits of evaporites on its floor that suggest that sometimes in the geologic past, the sea completely dried up. As water evaporates in these dry areas, the remaining seawater becomes saturated with dissolved minerals when then begin to precipitate. Because they are heavier than seawater, the minerals sink to the bottom or form a white crust of evaporite minerals around the edges of these areas. Collectively termed salts, some evaporite minerals such as halite, which is a common table salt, taste salty, and some such as calcium sulfate minerals, anhydrite and gypsum do not. So this is a picture of evaporative salts cover the floor of the seasonal. Death Valley, California. Now we have a different type of sediment which is cosmogenous sediments. Cosmos means which came from the universe and it is derived from the extraterrestrial sources. So what is the origin, composition and distribution of cosmogenous sediment? Forming a very small but important component of the overall sediment on the ocean floor, cosmogenous sediment consists of two main types, microscopic spherules and macroscopic meteor debris. So microscopic spherules, they are small globular mosses. Some spherules are composed of silicate rock material and show evidence of being formed by extraterrestrial impact events on Earth and other planets that eject small molten pieces of crust into space. These tektites, which come from the word tektos, translating to molten, then rain down on Earth and can form tektite fields. Other spherules are mostly of iron and nickel. You can see the image of a spherule here. How does it look like? And these form in the asteroid belt between the orbits of the Mars and Jupiter when asteroids collide. This material constantly rains down on Earth as a general component of space dust or micrometeorites captured by Earth's gravity. Although about 90% of micrometeorites are destroyed by frictional heating as they enter the atmosphere, it has been estimated that as much as 3 lakh metric tons of space dust reach Earth's surface every year, which equates to about 10 kilograms every second every day. The iron-rich space dust that lands in the oceans often dissolves in seawater. Glassy tektites, however, do not dissolve as easily and sometimes comprise minute proportions of various marine sediments. Macroscopic meteor debris is rare on Earth but can be found associated with meteor impact sites. Evidence suggests that throughout time, meteors have collided with Earth at great speeds and that some larger ones have released energy equivalent to the explosions of multiple large nuclear bombs. To date, nearly 200 meteorite impact structures have been identified on Earth, most of them on land, but new ones are being discovered on the ocean floor. The debris from meteors, called meteorite material, settles out around the impact site and is either composed of silicate rock material called chondrites or iron and nickel called irons. So this is it for this current lecture. Bye bye. See you next time.